So good afternoon all. I'm Sowmya from CDAC Pune. So today we'll be learning a few brief concepts of machine learning and deep learning. But our main agenda was to teach you about distributed training if you are aware of deep learning. But the thing is directly jumping into distributed training would be not a good choice. So we'll start off with machine learning and then we'll go to deep learning and then probably do our distributed training. So morning session, everything was regarding GPU and most of you all, like almost everyone uses Python, right? So now we'll be doing deep learning and we'll be offloading these deep learning models in our GPU and then we'll be executing it. Okay? So AI. If I may ask, what do you guys define AI as? Like, what is AI from your perspective? Anyone? Huh? Human assistance. Then? I mean, everyone is talking about AI right now, but why do we need AI? So if you have to define AI, AI refers to the ability of the software and robots to mimic the natural intelligence of the human. So anything that tries to replicate how we think and we, process things, if the machines do the same thing, then we define it as AI. But it is not like AI showed up all of a sudden now. It was back then in 1956, the term AI was already introduced, but no one really spoke about it. But now there is a sudden boom in AI. Everyone's using ChatGPT, LLM models, deep learning, machine learning. But why? So these are some of the main reasons why. First thing is advancements in computational power. So back then we had only laptops, which would not support all the models that we are currently running right now. Like you saw, we only had a laptop which had like quad core or 4 cores, which would not support such huge data and computation. That was one reason. And thanks to like major tech giants like NVIDIA and other companies who have done a very massive good job in terms of hardware. So there was advancements in computational power. That is one thing. The second thing is the explosion of data availability. I mean, since the internet was there and then we had access to a huge amount of data. So you're having clusters, but you do not have data. If you have a supercomputer, but you do not have enough data to train your models, then it makes no sense. But now we have data also. So that was another plus point. Coming to the breakthroughs in algorithms. So now we have clusters, supercomputers, we have huge amount of data. Now all that we need is an algorithm that uses both of these things and does the job for us. So that was possible, and that's when people started doing research and development in terms of algorithms as well. And then eventually industry started investing in this domain, and there was improvement in AI and research and infrastructure. And likely AI is now everywhere in terms of healthcare, finance, and autonomous vehicles and all other fields. Now, if we have to define what is AI, ML, DL, and Gen AI, this diagram represents it. So the very broad spectrum, if we consider, AI is a field of study of how the machines mimic human, and machine learning is a subset of AI. So what machine learning does is it tries to find patterns in your data. So we'll learn deep about it, learn in deep. And then comes the deep learning. Since there was few limitations in machine learning, we had to come up with something called as deep learning. In deep learning, we have something called as artificial neural networks, which helped us solve really complex problems. And then inside that, we had this now trending Gen AI, where generative AI, we could create new text, images, and everything. So these are some of the differences. Like I explained, ML is usually used to identify patterns from the data. DL is using neural networks and simulates how your actual human brain works. And generative AI is to create new content and images. So some of the example areas is when it comes to machine learning, you can relate it to your Netflix recommendations. And deep learning, most of them are like image-based operations like facial recognition and autonomous driving in real time. And then in Gen AI, you have ChatGPT and DALL-E. So for today's demonstration, I'll be using this cluster. Like Akash might have showed you a different cluster, which was from Delhi. So this is Param Shakti. It is deployed in IIT Madras. So this is the compute capacity of this particular node. It has 10 login nodes, 10 management nodes. CPU only nodes are 476 in number, and GPU nodes are 30. And you have high memory CPU only nodes, which is 96 in number. So when I tell nodes, I hope you guys understand what is a node. Yes? Yes or no? Yes. So this also he showed. So when a user logs in, you land in any of those login nodes. And through that, you will try to access any of the nodes that you want to submit your task. It can be GPU nodes, it can be CPU nodes. And if you have like any compute intensive applications to run, which needs higher memory, then you go for high memory nodes. So this is the infrastructure of architecture of the Param system. And the nodes are interconnected using InfiniBand, which is provided by NVIDIA. So there are some essentials of HPC cluster architecture that we need to be looking into. So this will be a very brief about HPC, and then later we'll move to machine learning, deep learning, and distributed training. So what are the essentials that we need in a HPC cluster? Firstly, it requires CPUs with high core counts. Like as discussed in the morning, we need more number of cores. Second thing, we need low latency, high bandwidth networking. Imagine you have two nodes connected to each other and it takes forever to transfer data. It makes no sense training your models on those sort of nodes. So you need to have a very fast, high bandwidth is what we define it as. So you need to have such kind of networking, which is InfiniBand. Otherwise, you can also use RoCE, RDMA over converged Ethernet. But currently, in all our NSM clusters, we use InfiniBand. Next is, when it comes to AI model training, we use something called as tensor cores. So these are efficient in running all your matrix multiplications that is mainly there in all your computation. And then SSDs. So if you are trying to run some very compute intensive tasks, it takes a lot of time for you to bring data from your storage to your GPU to perform tasks. So if you can somehow keep the data in your SSDs, then the operations is faster. So that is also another option that you can use. And next is the storage system. And we use Lustre as a storage system to keep all the files. So that is one more thing. When it comes to HPC focused container software, now we discussed about machine learning, like we'll be discussing about machine learning and deep learning. But the real problem what users face is to create the environment for this particular executions. So we have something called as containers, which creates an environment for you to run your programs. And you can easily port it to any other cluster, or you can export it, and you'll make sure that you will not affect the dependencies that is present in your user directory. So this is one added advantage of your container technology. Ideally, people might have heard about Docker. How many of you have heard about Docker? Yeah, so but usually what happens is in HPC, we do not give access to Docker. So there are few issues in Docker. It does give access to your system files. So we have an alternative that we use instead of Docker. We'll be discussing about that in later slides. Next thing is the Slum. Slum is, like we saw, it's the workload manager. It will be used for you to submit your jobs and monitor your jobs. And then comes PyAccess. PyAccess is a Slum plugin. Like I told you, since Docker is not allowed, we use something called as enroute. So that is an alternative that we use instead of Docker. And this PyAccess plugin will enable you to use that enroute with Slum seamlessly without any problem. So this is enroute. So it is unprivileged user space application. So it doesn't allow to access any root files. So this is preferred over Docker. And it has built-in GPU support. So you can directly run your GPU-based applications using this container technology. And it also supports your Docker images. Next thing is to create creating environment for your executions. We use Miniconda, a minimal installer for Anaconda. Here you create environment and you try to execute your programs. So for today's session, all the codes that will be executed is present in this particular Git repository. You can just open and you can look into the files. And meanwhile, I'll explain the theory and then later we'll go for the hands-on part. Coming to machine learning. How many of you have already executed machine learning programs and very well aware of how it works? Everyone. So I'll keep it very fast then. So machines find the pattern and input data. So ideally what happens in traditional programming is we give data and we give program, and then the computer gives us the output. But in machine learning, what happens is we give data, we also give the output, and the machine tries to find the pattern that generates that particular output. And when you give a new input, it will be able to give the output for that particular record. So we have supervised learning and unsupervised learning. Usually supervised learning, we do tasks like predictions, classifications. In predictions, we have all regression algorithms and classification algorithms. In unsupervised, mainly it's like clustering. The thing with supervised learning is that you need a labeled data set. What I mean by that is you need to have the output as well, a labeled output also. But when it comes to unsupervised, that is not required. And how does the machine learning work in supervised learning? Is it tries to learn and compare the predictions to the known outputs. Since we already have our outputs, it will predict the output based on the program, and then it will try to compare with the existing output that has already been present in the data set. And that's how learning happens in machine learning. Some of the examples are image classification, and in unsupervised, it's like market segmentation and stuff like that. So these are some of the algorithms that are mainly used in supervised learning, unsupervised learning. And there are a few challenges also in both the things. And when it comes to supervised learning, there's overfitting to training data. I'll explain what that is in the later slides. Typical output is to predict a label or value. When it is classification, it will usually predict what is the outcome. either 0 or 1 or like certain classes. Or if it's regression problem, some continuous value will be predicted. And when it comes to unsupervised learning, clusters and patterns will be identified. So if we consider the life cycle of machine learning, ideally we find the problem definition, we'll collect data, and then we do data cleaning and pre-processing, which is very important. And then we do something called as feature engineering and selection. And then we have what model to select for the particular problem that you have. And then you do your model training, and then you evaluate your model, and then you tune it, and then finally you deploy it, and then you'll maintain it. So coming to data cleaning and pre-processing. Data cleaning is a key step in ML for identifying and removing missing, duplicate, or irrelevant data. So there are times when you have data set with like empty values, and you have like duplicate values or some features which are not even required for your tasks. So those things all come under data cleaning. So what all removal of unwanted observations. There will be some columns in your data set which are not really required, and they'll just add noise to your model. So you can easily remove that. Fixing structural errors, standardized formats, and correct inconsistencies. So the standardization part happens when like you have a data set which has, imagine you have two features. One feature is in the range of 10,000s, and the other one is in some points, 0.1, 0.2. So this creates a difference when you're trying to do machine learning problems which uses this distance to calculate the distance between 2 points. So that will affect, so you need to standardize your data sets. So those kind of things come. And then managing outliers. So in your data set, you might have things like outliers, which are way beyond your normal data records. So that has to be detected and identify if it is error or it is actually a valid data point, because it will affect the accuracy of your model. Handling missing data, you can either impute it, like create an average of certain values, and then you can impute it, or you can like even remove those records. So this is what I was talking about. All the NaN values can be replaced with the average of that particular column numbers. And when you have something like dog, cat, and sheep, obviously your model cannot process text. So you can encode it. We call that as one-hot encoding, convert it into numerics. And then you have this outlier detection. If you plot the graph of your data set, you will be able to find out if there are any outliers. And then you can like figure it out if you have to keep the outliers or not. And this is about feature scaling, standardization or normalization. Like I told you, there might be features which have different ranges. One might be in thousands and one might be in like decimals. So to keep it in a certain range, we do normalization and standardization, which will improve the model accuracy. So some of the misconceptions of ML is that machine learning can solve any problem, but it actually depends on the quality of your data and the algorithm you have selected. And one more thing is ML always improves with more data, not really. So if the data quality is very poor, it doesn't have to be that way. ML replaces human input. ML requires supervision, especially in critical tasks. So I'll tell you why this happens later. So this simple explanation on how ML model train. If we consider a simple example of linear regression model, if we consider one output variable and one input variable will be your independent variable, and your output variable will be your dependent variable. So if I can consider an example. So if we consider this as our input variable, this will be our output variable. So this will be a regression problem. Imagine, consider this as like some radius of your pizza. And this is your price in dollars. So for every input, you have an output map. So now the real question is, if I give 4, what will be the price of my pizza? So this can be predicted by your linear regression model. But how will that do? So if you plot a graph, this is your y, this is your x. Something like this. Now, the real thing is, now you have to plot a line in such a way that the distance between these data points is minimum. So this is called your residuals. Now, if I give a new input 4, now what will be my output? That is dependent on where your line is drawn. So this will be my price for my input 4. So how is this? Now, the real question is how to fit this line. So that is when we have our, so here, this is our straight line formula. So when it comes to regression, here we consider this as weights and this as bias. So this is your input and this is your output. So how much your weight, the importance of your input feature depends on what your weight value is. And this bias helps you to fit your y-intercept in your straight line. So if you can see here, so W depends on how you will fit your line. The moment you change your W value, you will be able to shift your line up and down. And if the moment you change your bias values, you will be able to shift your line here through the y-intercept. So when you do training of your model, what happens is your W and B variables will be learned. And the best value of W and B will give you the best fit line for this particular data set. So what is the best fit line? The minimum error that, so this distance between the data points and the line should be minimum. So how to get the minimum value for that particular data set? So to minimize the error means to reduce the difference between the predicted y and the actual y. Now, initially we gave a set of value for W and B. We'll get a certain output that is called our y predicted. So and then what your data set already has is your y output. So the difference between these two, you will get your error. Now the real thing is how to minimize your error. If your model should be 100% accurate, then your y predicted and your y actual should be 0. But ideally in machine learning algorithms, getting 0 error is very difficult. So at least we need to make sure that the error is minimal. So this can be done using a loss function. First, we'll be calculating the total error using something called as loss function. And we'll try to minimize this loss function so that the error is almost near to 0. So when I tell loss, I'm defining it for one single record. So when I tell cost function, it is basically for all the records in the data set. So ideally, you have to find the minimum point of that cost function where the error is literally close to 0. So if you can see this graph, this is the minimum cost of the cost function where the error will be very close to 0. So we need to reach this point. So at what value of weight will your cost function reach minimum? That is what is to be learned. So the final question is, what value of W is the best to reach the minimum of that cost function? So ideally what we'll do, we'll give a random value for W. So when you give a random value for W, you'll be able to get a cost function, value for cost function. And for all the values of weights and costs, if you plot, you'll get a curve like this. So this is your ideal weight where the cost is very minimal. But when you're trying, how do you go towards that best value of weight? That is the real question. So what you will do is we'll use something called as gradient descent. So this is called an optimizer, which helps you how to change your weight values so that you reach to that minimum. Okay. So in gradient descent, we update weights and biases iteratively to minimize our loss and to reach the minimum cost or loss function. So to update these, we need to compute something called as gradients. So these gradients are nothing but the values that you'll be using to change your weights. These gradients are nothing but the partial derivatives of the loss function with respect to your weights and biases. So you will be getting your new weights and new biases when you actually calculate your gradients. And that's how your model will train. And here alpha is the learning rate. Now this, how fast it will reach the minimum, that is decided by this term called alpha. Coming to the model selection. When selecting a model, we distinguish three different parts of the data. Now, how data is distributed? When you get a data, you usually create a training set out of it. You'll create a validation set. So when you're actually training, it should also see how it is performing. So that part is taken care by the validation set. And then you have a testing set, which is unseen data. During training, you will not be showing this part of data to your model. So this is the linear regression that we studied. And then we have our logistic regression. So linear regression we'll use when we are predicting all the continuous values. So when you have to classify certain, imagine you have to classify based on some certain record if the object identified in the space is a star or a planet. So those kind of classification tasks, we use something called as logistic regression. So here you can see Z is equal to WX plus B. And this Z will be used in your sigmoid function, which is 1 by 1 plus e to the power minus Z. So what this algorithm will do is, if your output is more than 0.5, it will classify your record as 1, or it will classify, if it is less than 0.5, it will classify to the class 0. So that is how classification happens in this particular algorithm. Coming to another algorithm, K nearest neighbors. So in this, what happens is you have data points here. If you plot all the data points, Now, if you need to find the output of this new data point that you'll be placing in the graph, you will try to see what. So using this algorithm, you can do both classification and regression problem. So if you have to classify which point this particular data point belongs to, then you will consider your nearest points, and based on which of them belong to a majority of class, you will classify that particular point towards that. So here there are two purple dots. So basically, if your K is set to 3, then this will be classified to your purple group. And if it was K is set to 5 or something, then it would have classified to yellow. So this is how your K nearest neighbors work. So how does this calculate? So basically, when you place a new data point here, it will try to find the distance between the data points. And based on the value of K that you set, it will consider those many nearest points to decide which class it belongs to when it comes to classification. And when it comes to regression, it will take the average of those nearest neighbor data points, and it will give you the output for that particular new data point. So if this is the data set points, and the yellow dot is the new data point that you have placed, if you're considering your K value as 3, then it will be classified as that particular group. But if you're setting your K value as 10, then it will still be classified as that particular group, because the majority of the data points belong to that Virginica. And then when you have set your K value to 20, then it is classified it as Sentosa. No. It is classified it to green group. So the real question is, what is the ideal value of K that is to be considered? So usually it is defined that your K value will be ideal when your n is the number of data points, then square root of your n will be your ideal value for K. But still, K is a hyperparameter. You need to try different values of K, and then the best value that gives you the minimum error, that will be your best K value in this particular algorithm. Now coming to, there are many other supervised learning algorithms, but I'll not be explaining those in detail. Coming to unsupervised learning, here we don't have labeled output in our data set. Mainly here we do clustering problems. So this also uses the same distance matrix, that is the Euclidean distance. Based on the distance, it will try to group your data points in particular cluster. So how the actual working happens is, it will place something called as centroids. So how many centroids it will place? It is k number of centroids, which is again a hyperparameter. And then it will assign each data point to its nearest centroid, and it will form k number of clusters. And once you update these centroids by computing the mean of all data points in that particular cluster, and you keep repeating this until the point where the centroids don't change for the data points. So if we have to see a pictorial representation, so initially we are assuming our K value is 2. So we have placed two centroids. So we have placed 2 centroids. Now what it does is it computes the distance of every point from centroid and cluster them accordingly. So all these things are closer to this centroid, so it is considered as one cluster. And this particular data points are considered in this particular cluster. Now, after this, what it does, it adjusts this value of the centroid by taking the mean average of all the data points in that particular cluster. And the centroid is shifted. Similarly, this also performs the same operation, and this centroid is shifted. Now again recluster and every point based on their distance with the centroid. Now from that particular centroid, the distance to all the other data points is again recalculated to check if all the data points are still in their old cluster or not. So this keeps happening in loop unless and until the data points don't change their clusters. So when they don't change the cluster, it means that that is the end of this model training. See, again adjust centroids and recompute clusters and repeat this until data points stop changing their clusters. So this is how it actually works. You have X train where you don't have Y because there's no labeled target. And case the number of clusters to be created. And you find the distance of every point from the centroid. And then based on the closest centroid, assign the cluster number to every point. And then you calculate the new centroid for every cluster using the formula. And then all new centroids and old centroids, when they are like, they don't change their clusters, that's when you know that the model is trained. So that was something like very brief about machine learning. There are many other algorithms, but I'll not be going in deep with them. So there are more techniques that you can use to improve your model performance. One such thing is k-fold cross-validation. So in this, what it does is your data is split into k number of parts. And what we do before we train, we divide our data into training data and test data. So in this case, what happens is your train data and your test data will be shuffled accordingly based on your k number of parts. If k is set to 5, then your data will be chunked into 5 parts. Training and testing is done iteratively k number of times. And in each iteration, k minus 1 parts are trained and one randomly selected part is your test data. So this is one such technique to improve your model performance. The other one is data scaling. Like I told you, like normalization and standardization. If you directly use the data set, which has like varied feature values, some in thousands and some in 0.1 or 0.2, then it will actually affect your model performance. So if you try to standardize it, bring all the data features in the range of 0 to 1 or like from 1 to -1, then your model accuracy will improve. So that was a very little bit about machine learning. The real question is, everyone's using machine learning and most of them are happy with it, but why do we need deep learning? Any idea? Any of you here are using deep learning already? Yeah. Why do you think it doesn't work? Okay. Any other answers? So imagine I am not from astrophysics. I do not know how your data sets look like. Now, if you give this data set to me and tell me to train a model, you'll give me a data set where it has, I'll show you a data set, for example. Visible, right? So imagine this was like a synthetically generated data set. I'm just assuming this is how your data set might look like. Now you have, so if I have to identify an object in the space image, you would have got such values in your data set. Now, if I am not from this particular background, then I do not know what all features are important to classify it as a star or a planet, right? So it means that your machine learning actually needs domain knowledge, which means when you're doing feature extraction, if there are 10,000 features in your data set, and I need to only keep maybe 50 features. I need to know which are important, which are not important. Imagine I remove something very important, then my model will not perform well. So the problem in machine learning is that you need human intervention when it comes to feature engineering, which means that you need domain knowledge. This is one drawback of machine learning. And also when it comes to dealing with data sets like images, machine learning does not perform well. So that is why deep learning came into the picture. And how does deep learning solve this problem? So you can see in the slide, you have input. In machine learning, there is a manual intervention where feature extraction is performed. And then all that classification and regression happens, and then you get your output. But in deep learning, what happens is you don't have to define which feature is important, which is not important. The neural network itself will learn which feature is more important, and it will do the training. So this part is best about deep learning, and that is why people prefer deep learning. And it also works very well when it comes to images as your input data. If you're dealing with space images or something like that, deep learning is the best method to solve these problems. So in what all fields deep learning is present? So it is there in computer vision, mainly image-based data sets. Deep learning works really well. Object detection, your self-driving cars is nothing but your images are processed in real time and is updated. And then your NLPs, your chat GPTs, voice recognition, virtual assistants, your recommender systems, and many other fields. So how was this deep learning inspired? Basically, people thought of human brain structure, and that is how deep learning was inspired. So your deep learning is represented something which is called as neurons. It is basically inspired from your brain structure. So in your deep learning, you have something called as neurons, and your neurons look something like this. So what is the input for your neuron, and what actually happens in this is, now we are all aware of this y is equal to wx plus b. Similarly, you can see here there is wx plus b itself, and here x1 and x2, these are all your input features. Here x was single input. So when you have x1, x2, x3 and many features, so that is when you use deep learning. So this, every neurons will be connected to every other neuron, and then you will have a output neuron based on if it is a regression problem or a classification problem. So this is all, everything is connected to everything else. I'll show you the structure of neural network and how it works. So this will be your input. And this are your weights. During your training, like I told you here, what are the values that will be learned? Your W and B. So similarly, here also your W weights will be learned during the training. So these will be your inputs, and your inputs will be multiplied with your weights, and then it will be summed up and added to something called as bias. So here bias is denoted as W naught. And after this, there's something called as activation function. So what this thing does is it will introduce non-linearity in your problem. So in real world, all your data set and things are not in linear relation. So to introduce non-linearity, you use activation function and then you will get your output. So this is how your neural network looks like. So this is one such neuron, how it looks. And if you use many of these neurons, this is called a multi-layer perceptron. So this is a single perceptron. We call this as a single perceptron. And when you use a hidden layer, like another layer in between your output layer and your input layer, it's called multi-layer perceptron. So what basically happens is you have your input layer. So all your input values will be multiplied with your weights and your bias will be added and it will be processed by the activation function and that value will be sent to the next layer. Now, why is this hidden layer present? So this adds, it is used to bring out, find out patterns of more complexity. The more number of hidden layers you introduce, it will be able to identify more complex problems. And what is the ideal number of neurons in a hidden layer? That is actually not known. So that is called as a hyperparameter. So you will have to do trial and error to find the best optimal number of neurons to be set in your hidden layer. So you can see here, there are three hidden layers. So all your input values will be multiplied with these weights. And then the bias will be added and then it will be going through the activation function and it will be given as input to the next hidden layer. So the same thing repeats until you reach the output layer. Now, if it is a classification problem, then your output layer will have two neurons in it. So based on if you have 0 and 1 as your class output, so if it is like you're trying to classify an image as apple or mango. So if it is your output is 1, then it will be classified as apple. And if your output is 0, it will be classified as mango, something like that. Like I told you, there are different types of activation functions which will make your model to, it will introduce non-linearity in your model. So one such commonly used ones are ReLU when it comes to image processing. So what it does, if you get a value that is more than 0, it will keep it intact. But if you're getting some negative values, then it will set it to 0. Set it to 0 in the sense, now imagine this neuron got a value from this particular neuron. If its value was 1, then it will pass that value to the next neuron. But if it was something like -3, then it will pass 0, which means that this neuron will become deactivated. So there are different types of activation functions. So you can decide like which activation function best suits your algorithm. Mostly for image-based algorithms like CNN, neural networks, we use ReLU activation function. And in the last layer, we use sigmoid because it will give probability between 0 to 1. So you can easily classify it as 0 or 1. So like how we studied how learning happens in your linear regression, right? Your W and V will be learned. So based on that, this line will shift and adjust itself so that this distance between the points are minimum, which means your error is minimum. But in 3-dimensional, when you're plotting your data, your X is not a single dimension. You have n number of X inputs. So if in 3 dimension, your plot will look something like this. And your aim is again similar to find the minimum of this particular function where the error is 0. So that thing is again calculated by your gradient descent, where it will find out the minimum value of error, where your y predicted and your y actual, they will almost reach 0. So if I have to explain in terms of how this neurons work, so there's something called as forward propagation and backward propagation. So in forward propagation, like I told you, your inputs will be multiplied with your weights, your biases will be added to it, and then passed to activation function. And finally, you will calculate the loss. Now, to reduce the loss, what you do something called as back propagation. In back propagation, what you do is you will adjust these weights. Means your weights are not correct, that is why you got an error. So if you try to adjust these weights, then you will get a different value. The error might be more or it might be less. So this is when you know what values of weights you should be adjusting. So the adjusting of weights will be done by something called as optimizer. Okay, so that happens in your back propagation. Now here your input values will be passed to the neural network like this. And then it will be, again, like those calculations will perform. And for example, forward propagation. Now here you might ask me, what is 781? If I consider an image of 28 cross 28 pixels. Now, how do I feed this to my neural network? Your pixels are nothing but numerical values. So if you flatten it, your 28 cross 28 will be your 721 neuron inputs. 781, 84 neuron inputs. So each values in this, see, if this is a grayscale picture, it will range from 0 to 255. And if it is a colored image, then it will have RGB. It will have 3 different matrix like this. For simplicity, we'll consider only grayscale image. So your 28 cross 28 grayscale image will be a 28 cross 28 matrix, 2-dimensional matrix. Agreed? So if you give this as input for your neural network, so you will have 784 inputs to your neural network. So each neuron x1 will be your pixel value of this first pixel of the image. So that is how you got your 781 inputs, 784 inputs. So similarly, now what is this? So imagine we are considering a data set of handwritten numbers. Handwritten numbers from 0 to 9. Now when I'm giving a model to train, if I'm giving a new image that I'll write 8 or something, it should be able to find out what number it is. So ideally, when I'm training, what happens? Now if it is considering 5, that 28 cross 28 pixel will be given as input as my 784 neurons. And this thing happens and it will predict if it is any number 0 to 9. So if it predicts it as 5, which means it is correct. But if it is not predicting it as 5, it means that there is error. So that is when back propagation happens and your weights will be adjusted unless and until your 5 image will actually be predicted as class 5. Any questions till now? I'm not going into the mathematical complexity, but at least the vague understanding of how things are working. If 784 is nothing but your pixel values in a 28 cross 28 image, consider it as that. And if that image, it's able to predict whatever number that is. So if it is taking 0, it should be able to predict 0. And everything, all the other neurons should be, values should almost be less to 0. So that's how prediction happens in deep learning. So So likewise, the cost function, you need to find the minimum point where the error will be minimum so that you don't have any difference between what is actually predicted and what is the actual output that was present. Now there are few hyperparameters that is present when you're dealing with deep learning. One is the number of hidden layers. Now you can see here, there's only one hidden layer. Here there are four hidden layers. Now how do I know that my model will perform better if I just add one layer or if I add 4 layers? That is actually not known. So you will have to do trial and error to get the best number of hidden layers. That's why it comes under your hyperparameter. And the number of neurons per layer, that is also hyperparameter. But your input and output layer will remain constant because your input layer, if it is a 28 cross 28 matrix, it will definitely be 784. And your output will be 0 to 10 because your data set is having numbers ranging from 0 to 9. But this middle, how many numbers of neurons should be in your hidden layer, that is again not known. So this again is a hyperparameter. You will have to do trial and error to get the best possible accuracy for your neural network. Again, learning rate. So what is learning rate? Like I told you, whenever you try to reach this minimal point in a function, how fast, how much change you should do on your weight so that you reach this point faster, that is decided by your learning rate. If your learning rate is very big, imagine this is your point that you're at. If you keep a higher learning rate, it will directly jump here or it will go beyond this thing. So keeping a proper learning rate also matters. So slowly it will try to converge down to this point. If you keep a huge learning rate, then it will go beyond your global minima, which will again increase your error. And then optimizer. Like I told you, the weights are updated using something called as optimizers. So these optimizers are responsible for calculating your gradients. Like gradients in the sense, just consider what changes I have to make in my weights to make it closer, to make the loss closer to 0. So epochs is nothing but now you have an entire data set and you have a neural network. When your neural network, here in this case, is just one image it processed. One image to process, it took 784 neurons at a time, one record, which is 5 images. So in a data set, I have 70,000 images like this. Once it processes all the 70,000 images like this, then I'll consider that one epoch of my training is done. So that is what epoch is defined as. Full passes over the entire training data set. That is called, I've trained one epoch. And then your activation function, like I told you, to introduce nonlinearity in your function, in the model. And then batch size. So there are times when your GPU consider, it might not be able to handle. Now, since we are dealing with images, it cannot handle 10,000 images at a go because your GPU memory is limited. Usually now the NVIDIA cards that we get, if you consider Ampere series, NVIDIA A100 card, it will have a maximum memory of 80 GB. Beyond that, you can't load images in your GPU memory. So you need to, if I'm directly loading 70,000 images in my GPU memory, it will give me CUDA out of memory error. So what we'll do is we'll do something called as batch sizing. So we'll give only little by little data. We'll try to do forward and backward propagation. And then we'll again accumulate the gradients. And then finally, we'll do it for the entire data in terms of batches so that we don't have to directly put the entire data together to the neural network. So this is what I was talking about, feeding an image to an artificial neural network. So when the image changes, that particular number of neurons will be processed, and that particular class will be, it will be classified to that particular number. If you're giving 9, then it's supposed to give highest probability for the neuron 9. This should get activated. And this all, the values should be minimum. And if it is 0, then this probability of this should be high. And rest everything should be almost close to 0. It means that the model is trying to tell that this image that you have given to me is value 0. So before going to CNN, we'll try to see how these things are implemented in code. So we'll do a little hands-on. How many of you have access to Colab? Google Colab, yeah. Oh, if you have access to Colab, you can directly use Colab. Otherwise, morning session, people have access Kaggle, right? There also you can upload the notebook. So if you go to this Git repository that I've mentioned, were you all able to access this Git repository? Yes? No? Okay. If you go to the introduction part, you have a little overview about what you'll be doing in the introduction part. You have few explanation about slum. So for someone who has never used cluster, you can go through this. What is slum and what are the common terminologies that is used in slum? What is a compute node? What is a socket, core, thread? And when you submit a job in slum, you will get certain flags like this, and what it means, everything is being explained here. How to submit a job, how to check your job status, all the commands are present here. And there's something called as modules. So this is a cluster that I've logged in. It's actually in IIT Madras. So if I do, so there are a few HM nodes, there are GPU nodes and a lot of CPU nodes. And people are actually running their jobs here. Yeah, module. So if I'm a new user and I do not have access to install packages in this cluster, all I can do is I can do module avail. So what this module package does is we as system admins, we already install packages for people, for users. So you in this particular cluster, there are so many packages that is already installed. So you can directly just load any of these things and start using. The moment you load this particular module, you will have that particular environment in your user environment. You don't have to externally install PyTorch, TensorFlow, whatever. Here you can see there are modules, PyTorch GPU, TensorFlow GPU. If you have any codes that run this particular programs, you can just directly load it and use it on the go. So that is about modules. And how to write a slum script. If people are very new to using a cluster, then how to write a slum script, how to run your basic Python command Python program .py file if you have. So usually we'll provide something called as Miniconda. You can see here this Miniconda module is already present. You just have to do module load Miniconda in your slum script and you can run your Python script there. You don't have to create any environment, not set any variables or any Python variables. Here you can define what partition you want, how much time it takes and everything else. So when you're trying to run your Python code on GPU, then you mention your partition as GPU. And there are other troubleshooting explanation. You can go through it later. Again, modules. Like I told you how you can use modules. Just in case if you get access to the cluster, you can try out all these commands. There's also a cheat book where all the slum commands are mentioned here. So you can go through it. These are the flags that you will be using in your slum script. So this classifies a simple logistic regression program. It is a IPYNB file. So you can directly download this and you can try running it on your Colab or Kaggle. So what is this? Basically is a classification problem. What it does is it tries to classify an object if it is a star or a planet. So I created a synthetic data of around 5 lakh records where this is how your data set looks once it gets generated. Spaceobjects.csv. So it has these features: brightness, radius, mass, temperature, date of observation, distance from Earth. So if this is how your data set looks, how do you try to classify the object as star or a planet? So I'm printing the first 10 rows of my data set. Print data.head 10 to just show what the data set looks like. And now I'll be using sklearn. Now here I'll be extracting only few features from that particular data set. As per my knowledge, I feel like date of observation and distance from Earth is irrelevant to classify it as a star or a planet. So I drop those two features. So I'll add these columns in my X input, and my Y will be either it is a star or a planet. So if it is 0, it is planet, and if it is 1, it is a star. So all your X input values will go to your X data, and then all your output variable, that is planet or stars, will go to your Y. So now I explained that in your data set, it will be divided into training data, validation data, and test data. Now what I have to do is I have to split my data as training data, testing data. So you can see here xtrain and xtest. Xtrain is all your input variables for training, and xtest is for your testing. So you split it based on 0.2 is your test size. It means 80% of your data is gone for training and 20% is remaining in your test. So one best part is you directly have logistic regression function defined in this. So you can directly use it. And when you do model fit, there's also scaling done. Like I told you, here you can see the features. Everything is in 5 point, 6 point, and 5 point. And there is temperature which ranges in thousands. So to bring all this in a similar range, we do something called as feature scaling, that is standard scalar. Now this would have brought all the data points in a similar range. Now we'll give that to our logistic regression model and we'll fit it. After fitting, the training will be performed and then we'll get our Y prediction for all the test data. So the training would have been performed with xtrain. Now with the xtest, which is already scaled, we'll try to predict what values it is predicted. Now for example, what I'll do, I'll give a new value if this are my input. Now the main idea is what my model should be able to give me the output when I give a certain input. So if I give this as my input, my brightness is 0.8, radius is that much, and mass is that, and temperature is that, then what will be my output? Will it be a planet or will it be a star? So again, you perform a scalar operation on that, and then you give it to the prediction. So now it will predict. If it is set to 0, then it means that it is a planet. And if it is set to 1, then it is classified that particular data point as star. So this is your normal, and this part does the evaluation part of how good your model is trained. You can see that the accuracy is 0.97. And it has classified your models with that much accuracy. So you can play around and try giving a different values. You can see if it is, or you can also, if you want to verify, just give the exact same values and see if it is giving the same class or not, if it is a star or a planet. So this is a normal, very basic logistic regression that you can write. But now coming to deep learning. So in that particular Git itself, you have something called as Introduction to Deep Learning IPYNB file. So this is what I was talking about. We'll be doing image classification with our MNIST data set. So this data set has 70,000 images. It is 70,000 handwritten images. So it is all data set which consists of all handwritten images, which ranges from 0 to 9. Now our main goal is that our model should be able to detect if the image that we are giving is what, like if I'm giving a number 9, it should be able to predict it as 9. So that is my aim of training this particular model. So how do we do that? So this is basically the hello world of deep learning. We'll be using PyTorch. PyTorch is like a framework that we use for all deep learning programs. If everything is explained in this particular notebook, so if it is difficult, you can go through line by line and why each and every line is used, because it will take a lot of time if I go in deep. So these are some of the import functions. So torch is used to use all my PyTorch libraries. Torch.nn is to use to create, build my neural networks. Like this, whatever I created, that neural network layers, this particular function will provide me. And some of the data sets are already present with PyTorch. So that is defined in my data set. So that is why I'm importing that. And there are few helping libraries like data loaders to load my data. And you have optimizer, like when we discuss gradient descent. So like that, there are many other optimizers. Adam optimizer is one such thing. This optimizer is best, it performs better than gradient because it adjusts its learning rate also accordingly. So that is one plus point. And then there are other libraries and functions that we'll be using. So for that, I've imported. So you can run this and make sure, because this should be run, this should be executed on your GPU. Make sure you change your runtime to GPU. Make sure it is set to GPU. I'm using Collab. If you're using Kaggle also, I think there is option to change your runtime. Make sure it is set to GPU. So if you, after you set it to GPU, if you run this line, so device is equal to torch.device, CUDA if torch.CUDA is available, else CPU. So like you, in the morning session, you saw like for offloading things to GPU, like there were so many steps. You try to copy and everything. But here, you can easily offload everything to GPU thanks to frameworks like PyTorch. They've made it very easy. So first, to detect if your GPU is available or not, you can use this torch.CUDA is available to check if your GPU is detected. So if you get the value CUDA, it means that your GPU is detected. If CPU is coming, then it is not using GPU. So please make sure CUDA is printed there. Then there's a lot of explanation regarding what data set is used. It's a 70,000 images of all grayscale, black and white images. I've kept it black and white because if it is colored images, then it'll actually be 3 different channels, red, blue, green combination. So it'll get complex. So it's just 2-dimensional matrix when it comes to grayscale. So training and validation data labels, like I told you, we'll split the data before we are training. So similarly, X train, Y train, X validation, Y validation, and then we'll have testing data also. So first we'll be downloading the data set. Since it is already present in their datasets.mnist, you can, if you run this, it'll get downloaded. So you have your 70,000. So it gets downloaded here. If you're getting error, probably this value would have been set to false. Just set it as true and you'll be able to download the data set. So once you download it, you have segregated it to train set and validation set. So if you run this train set, you'll be able to see. So I told you it is a total of 70,000 images. In that 60,000 images are training data. 10,000 images are set to validation data to check if the training is performing correctly or not, to validate basically. Now to see how your data set looks like, if I take one single input output variable and if I run, so train set, so what will this train set consist of? It should be consisting of your input, which is nothing but your image, and then output will be, what is that image? If 3 is your image ka picture, then your output should have the value 3. So you can see here, if it's x of 10, if it is 3, and your y of 10 will be 3. You can play around here, you can check if it is 34, the image is 0 there in that particular record, and your y of 10 will also be 0. So this is what is present in your data set as of now. So prepare image for training. Now, if we cannot give directly the images to our model, so what we do is we convert these images into something called as tensors. Tensors are like n-dimensional arrays, like they perform really well on GPUs. So what we'll do, we'll convert all these input data into tensors and then we will perform the operation. So we are using So if you transform it and then you try to print the data type, so this is basically used to convert your image to tensor, and it is also normalizing it within the range 0 to 1. So this is both done together. So it is also converted it into a tensor and its value will range only from 0.0 to 1.0 for easy computations. So you can see a minimum of that tensor will be 0 and maximum will go up to 1.0. So none of your data values will be beyond that thing. So it will be very easy for your model to calculate operations. So in PyTorch, the dimension of image tensor will follow this format: C, H, and W. C is the number of colored channels, H is height, and W is width. Since in this case it's like grayscale, your C will be set to 1. If it was colored, then it will be 3. So here if you check, since it is grayscale, it is 1, 28, 28, which means each of your image is 28 cross 28 two-dimensional matrix, which is your 28 cross 28 pixel image. So what is stored inside that? If you see, it's all decimal values that range from 0 to 1. So when you try to check where is it placed, then you will be able to see that it is in CPU. So to move it to GPU, all you have to do is you can use this .CUDA method. You will be able to move it to GPU. It's as simple as that. Now there's certain transformation that we'll be doing on the training and validation data set to make it work efficiently on our GPUs. And there are something called as data loaders, which will help you load your data efficiently for your GPUs. That is also predefined functions. You can just use it and then pass your train set and validation set to it. It will manage how to send data to your GPUs. So we have train loader and validation loader ready. So here I told you, like, than giving the entire data set at once, we will be giving in terms of batch sizes. It means that I'll be sending 32 images at a go, not the entire thing. And shuffle is set to true, so it will shuffle and it will give 32 of it to the train loader. Now building a model. Now we were talking about this neural network, hidden layers, and how to build those layers. So first, what we have to do, we'll define layers. Now, what are layers we should have? First is a flattened layer that converts multi-dimensional input into one-dimensional vector. So like I told you, our input is always single dimension. X was like 784 input values. So before giving this value to your neural network, you have to make sure that your data set is flattened. So you will get a one-dimensional vector. So then that will be your input layer, which serves as a first layer of your neurons receiving the input data. And then your hidden layer, which I told you is a hyperparameter. This, how many ever layers you want, you can play around and see the accuracy might change based on how many number of hidden layers you have for your model. And your output layer, this will be predefined because you have only 9 numbers in your data set, 0 to 9. So that is 10. So this is the test matrix that is present. So when you flatten, this is how. So it didn't happen. So why didn't it happen? Neural networks are designed to process data in batches. So like everything is explained. Now you can like go through it in detail. So when you use this flatten function, which is provided by PyTorch, now this two-dimensional matrix was converted into a single dimensional tensor matrix. So this is how your flattened layer works. Now this will be my first layer, right, in my neural network. And then my input layer, the size of the input, since our images are flattened, the input size is determined by multiplying the number of channels. If it was 3, 3 into 28 into 28, it means we had a colored image, but since it's grayscale image, it's just 1 into 28 into 28. So now our input layer is also done. Now this is my linear layer where 28 cross 28 cross 1 neurons are entering, and then there is 512 neurons in my hidden layer. It means that the second layer, what I told, which is randomly I've taken 512. If this is my 784 input 28 cross 28 first layer input layer, in this hidden layer, I'm considering 512. So this is not a predefined number, it can change. And then, like I told you, we'll use activation function to introduce nonlinearity. Here ReLU is used. So if you're getting any inputs in negative, then it will truncate it and it will be set to 0. So since your hidden layer is 512 neurons, so your first layer should be giving out 512 outputs. So this is how your hidden layer is added here. And then your ReLU, again, you'll again introduce nonlinearity. You'll again add ReLU activation function for that particular hidden layer also. So here you'll be passing your input to these 512 neurons. Then here you'll have ReLU function where if it is values are coming in minus, then it will all be set to 0. It means that this neurons, some of them which are 0 will not pass anything. So again, there is 512 neurons here, and here again there is ReLU function. So if there is any negative values, then these neurons will get cancelled out. It will not pass anything. And last is the output layer. Since we have only 10 digits, 0 to 9, our n classes will be 10. So this will be our layers: a flattened layer, input layer, a linear layer with our input dimension size, and then our hidden layer with 512 neurons. And that 512 neurons is again finally giving out 10 classes. So whichever class will give the highest probability, it means that my model is predicting that as my output image. So we have defined the model now. Now how to compile and assigning it to a model. So you pass that to n.n sequential function, and this model will be passed to my GPU because I want it to run on my GPU. So you can see here input features is 784, and then 784 will give out 512 values. Again, these 512 values will be passed through this ReLU, and again 512 hidden layer neurons are there. That will again be passed through ReLU, and then finally I'll be getting 10 outputs. In this, the highest probability one will be classified as my image. So torch.compile will compile our model. And now, like I told, okay, now the layer is done and everything. But we also told that some training should happen, like the weights should get changed. And the thing that does this changing of weights is called an optimizer, I told you before. So we need to define a loss function also and optimizer also. So that has to be defined. So here we are defining a loss function called cross entropy loss. So this loss function is used in classification problems. There are many other functions, but for this particular task, I'm using this loss function. An optimizer, like I told you, like gradient descent, Adam optimizer is also another optimizer. So I'm defining that as my optimizer. So based on that, it will change my gradients and it will change my weights, and that is how my learning happens. Now, how do you train your model? So you have model.train function. So for x and y in your train loader, you will send both x and y to your device. And here if you see, you can see that optimizer.zero grad, it means your gradients will initially be set to 0 before your optimizer calculates any gradient values. Initially it will be 0, then later after calculation, that values will will change your weights. And here loss function will compare your output to your actual y values. This is your y predicted, this is your y actual, which was present in the data set. And then I told you, once the loss is calculated, the back propagation happens. That is when your optimizer will come and it will calculate the gradients, and this is how your training happens. Now, based on what is the difference between your prediction and your actual y values, you will be able to find out the accuracy of your model. So here you can see that you're calculating the accuracy output with comparison with your y. Now, how do you train your particular model? Like I told you, if it is gone through the entire 70,000 images in your neural network, then that is called as one epoch. But if I'm running the entire data set through my model 10 times, then it will be considered as 10 epochs. So I'll be training my model now for 10 epochs. It means entire 70,000 images will be passed through my neural networks 10 times. And then my loss and accuracy will be calculated. So this is how it is defined. Epochs is defined as 10. You can keep it 5. So the more it learns the data, the more efficient it becomes. So this number of epochs is also a hyperparameter, like we saw in the previous slide. Doesn't mean that you put your epochs as 10,000, it will pass through your entire data set 10,000 times. It doesn't mean that your model will perform well. So there is an ideal value for epochs which you will have to identify. For now, time being, we'll just set it to 5. So it will run through the entire data set 5 times and it will train and it will validate it. So you can see now the training is started. So this was some error from their side, not enough SMs to use. So there are some, if you're giving a lot of data to your GPU, there are times you will get CUDA out of memory error. It means that your GPU will not be able to take so much data. If there is no error, then your training will start. So you can see in 0 epoch, your train loss was so much. So as the main aim is your loss should reduce. Loss is nothing but your error that is being generated from your model. So as the number of epochs goes by, your loss should reduce and your accuracy should increase. So 5 epochs is completed. It means that my neural network now went through 70,000 images 5 times. So this happened in your GPU. Imagine running it on your laptop. So now to check if the prediction was correct or not, we will check that and see. So if you see the output here, you can see all the other values are in minus, and there's only one value that is in 7.8. Like I told you, the prediction of the output neuron will be highest on which class it will belong. So since it is 0, the value for your first tensor value is high. So it means that it classified it right. So this is one such hello world program to your deep learning training. You can play around and you can try on different things. You can also try to send a different value and check if it is predicting properly or not. Or you can try to increase the number of epochs and see, or like reduce the number of epochs, maybe the errors will be more. It might misclassify. So you can play around all the hyper parameters that I told you. You can change batch sizes. You can feed a lot of images at a go and then see if it is working. So all these things you can do. And this was your hello world of your deep learning. Do we have a break now?